In this session, we will be dealing with the second part of combinational logic design. Namely, we will talk about the functions and functional blocks and the basic rudimentary logic functions. Then we will take a look at decoding using the decoders and implementation, and encoders and multiplexers, and finally the demultiplexers and some design issues with them. So what about these functions and functional blocks? And these functions are you use them again and again, like your useful toolbox, okay? And they are called the functional. In the past, they were just packed together with small scale integration, for example, and here we talk about tens of transistors like this, roughly, and medium scale corresponds to hundreds of transistors, and large scale integration corresponds to 10,000s of transistors, for example. And today we're dealing with usually very large scale integrated circuits. They're called the VLSI circuits, and also there is ultra large scale ULSI integration, where you talk about millions of transistors packed in a single unit. There is also wafer scale integration and system on chip designs, where you try to reduce the costs, again having a layered structure in it. But this is out of the scope of this lecture, of course. But the idea is creating those blocks and using for your designs. This is the basic idea. Now let's take a look at the rudimentary logic functions. Here you see if the functions of a single variable x, and that's it. What you have here is just okay, these are just equal to your 0 and your 1, and when you connect them to the ground, it would be it would correspond to 0, and when you feed it with voltage 5 volts, it would correct to logical 1, and here you see an inverter. That's it. That's all you can have with those functions of one variable. Now suppose that you have multiple lines of information here, like bits, and if you have, for example, 4 of them here from F0 to F3, you can combine them together to represent them as a line, like bus with size 4, for example. You show it like this. This just explains us that it is a bus, this line. And then from that bus you can take out some particular lines. For example, you just take 2 of them out from here, for example, in this example C, like from 2 to 1, F 2 to 1, you take from here and you represent it like this. So this would be a smaller bus with size 2. What you have here corresponds to these 2. And you can also take out 3, for example, in the D part, and this would be this one, because you separated with a comma, and from 1 to 0 you take them, and that's it. Again, those will be a smaller bus that you take out from your main bus. That's how you combine information as a bus signal, and that's how you take out some information lines from that bus as well. And what about the enabling function? Enabling permits an input signal to pass through an output. Otherwise, it would be blocked by the enabling circuitry. And disabling blocks an input signal from passing through an output, replacing it with a fixed value. This is how we do it. And if you have 3-state buffers, in this case, the value on the output when it is disabled can be read as high impedance. and that's it. Here you see an example of enabling with an AND gate, for example. Okay, if you provide here 0 signal, for example, the output will be strictly 0, independent from the value of your input here. See? That's it. And when you give here 1, it means that it would be enabled. Then your output will depend on your input. That's it. It means that you would let the input signal to pass through that gate. If you want to implement this with an OR gate, for example, how can you disable this? You can just send here 1 signal, right? So it means that the output, no matter what, will be 1 in the lower example here in B with the OR gate. So you provide here again 0 signal, means this is disabled and the output will be fixed. No matter what you put here, you don't care, because the output will be locked and fixed. And when you send here, for example, 1 signal, this would be 0 and your output would be strictly dependent on X signal, and it means that now it is enabled. Okay, that's the idea with the enabling functions. That's the basic idea, and we will use them again and again. Okay. Now, what is decoding? We have 4 different types of approach here. We will see all of them: decoding, encoding, multiplexers, multiplexing, and demultiplexing. We will see all of them, and the first one is decoding. This is important because decoding is used in multiplexers and demultiplexers strictly as well. Encoders are another story, okay, but the decoders are the basis of multiplexers and demultiplexers, so they're very important. It's very important to understand this concept. So decoding is the conversion of an n-bit output code to an n-bit input code to an n-bit output code. So it means that if you have a, let's say, a 3-bit code like this, you can go ahead and have represent them in up to, let's say, 8 different output decoded strings of information. That's it. They are called N-to-M line decoders, and you can have here maximum 2 to the power n or fewer minterms for the input and for the n input variables here. That's the case. So let's take a look at some examples of different size, starting with the most basic one, 1 to 2 line decoder here. What you have here is, and if you provide here 0, for example, okay, these are equal signs, okay, there is stuff in okay, and if you provide here 1, this one will be selected and this one will be not, and if you provide here 0, for example, this one will be selected and not this one. Okay, that's the idea with the basic 1 to 2 line decoder. Okay, how about, and this is the truth table here, and how about a 2 to 4 line decoder here? Here you see the truth table here like this. You see this diagonal here. At any given time and at any given input combination, only one of the outputs will be 1 at any given time, and the remaining ones will be 0. How can you achieve this? It is again like connecting 2 1 to 2 line decoders together. So look at this. In fact, you have here this one, and you have here a signal coming here. What is this one? A0 here, and like which one? This one, like you see. So it means that you have here A0 switching, okay, where your A1 not is constant here from these lines. So you have 2 1 to 2 line decoders connected together here with all possible combinations at any given time, and these will be the selected outputs. Okay, if you provide here for example, let's say 1 0, okay, 1 0, if it means that you will have here 1 0, which is your index number here, will be 1. The remaining ones will be 0, no matter what. You see, it's obvious from the, let's say, structure or from the design. That's it. So whenever we want to expand those decoders to have larger decoders, so we start from the total number of input and outputs and try to go back and implement them with smaller packages of decoders. That's it. And for example, if you want to build a 3 to 8 line decoder, for example, so split them in the most logical or most efficient way, like for example in the middle or something. Like you can implement this. It's obvious that with a 2 to 4 line decoder and 1 to 2 line decoder. And what is in a 2 to 2 line decoder? There will be 2 1 to 2 line decoders again. That's it. So when you implement this like this, the solution would be pretty straightforward. Like you see, at the output, you need to have the, okay, it is 3 by 8, 2 to 8 line decoder here. It means that you will have an 8 AND gate level here for the outputs, and you need to have 3 inputs for that box. Okay, it would look like this: 1 2 3 4, 3 4. That's it. And what is inside that box will be your design. Okay, this is your basic 2 to 4 line decoder. So it means that you have these ones, and they will be connected with the inverted output or inverted input of A2 here in 4 of them, and these will be combined with this one, and these will be combined with the normal A2 as well, directly, and that will give you another 4. And then that's the idea with the decoder expansion. Roughly, you can implement any type of expansion in this manner. For example, suppose that we're trying to do a decoder expansion to 7 to 128 line decoder, for example. We want to have this structure. Let's try to do this together, okay? The closest possible split is like this. We first have to split this, like the 7 inputs here. Both of them should be close to each other when you split them. So 4 by 3 split is the best, and the resultant outputs will be 16 by 8. As you see, when you multiply them, you will get 128 as well. It would be your last level of AND gates. But before this, you will have 4 level AND gates. 4 AND gate level in the upper part, and 3 AND gate level in the lower part. That's the idea. And you can also go ahead and split this 4 by 16 decoder into 2 by 4 and 2 by 4 decoders. And those 2 by 4 decoders will be split into 2 1 by 2 decoders as well. Now let's take a look at how we can do this together. So what we're trying to do is a box like this, like we want to have a 2 by 128 decoder here. This is what we're trying to do. 1 2 3 4 5, okay, 7 inputs here, and you will have 128 outputs here. Okay, what is in this box? That's the question, and we will try to design that box here in this case. Okay, now, okay, how we can do this? We will have a level of output AND gates where you will have your 128 AND gates here, and they will be split like what? Like you need to have a Okay, like it's a bit large. Okay, you will have a level of 4 and like 16 AND gates here and 8 AND gates here, right? This will be your 16 AND gates, and this will be your 4 AND gate level here, and this would be the output of your let's say like a 2 by 4 decoder, right? I'm sorry, not 2 by 4. What's 2 by 4? 4 by 16 decoder, and this would be the output of, let me use another color here, your 3 by 8 decoder. Okay, this is how you combine them together. And what is in this 4 by 16 decoder? There will be two 2 by 4 decoders. It means that you will have a level of 4 AND gates here, a level of 4 AND gates here within this one, and you will have a level of 4 AND gates here and a selection input here and nothing else, like okay, connected like this. Okay, okay. Then these ones will be coming here and they will be multiplied with each other, having you 8 AND gates. Okay, this is not 4, I'm sorry, this is 8, of course. Okay, this is 8 because it's, see, 8 AND gates, and these will be combined together here in these structure. And what is in them, in these 4 level, it would be your, okay, like you will have 2 combinations of inputs here for this one, and it's 2 1 by 2 decoders. You will have here what is inside. You will have another one here for the remaining ones, and they will be, okay, multiplied together here, like not multiplied, ANDed together here, and these will be ANDed together. And again, for this one you will have this, for this one you will have this. Lovely, beautiful, you see. And oops, I made a mistake, I'm sorry. This one should look like this, right? And this is the my structure. Okay, all right. So what I have here will beautifully look like this. Okay, you will have your A6, A5, A4, A3, A2, A1, and A0 inputs here, and this will be your out, and this is your like 128 outputs here. And when you pack them together, like in this box, like a functional block here, it means that you will have your 7 by 128 decoder as beautiful implementation like this, which is very convenient, and it makes life easier for us when you want to design it on, even in a laboratory hands-on experiment or by any computer aided design. That's the idea with the decoder expansion. Now, if you want to design a decoder with enable, we just discussed enable a few moments ago, and I hope you have an idea about it now. So what we're trying to do here is, if we override this circuitry with a signal, with an enabling signal, suppose that it is this signal. If it is 0, for example, it's not enabled and the output will be fixed. It will not work at all. That's it. And if it is enabled, it will work as a standard, for example, decoder as well. Now, what you see here is your basic decoder. You see how beautiful it is? And now, if you want to have an enabling level here and provide this with an enabling signal here, if it is 0 here, it means that all your outputs would be 0. No matter what input, what you select here, it doesn't matter. You see, it is given in this part. Okay, this is how you make enabling. And When your enable is 1 now, your decoder will function as it is directly. That's it. Now, we're done with decoder with enable, but in fact, if you provide here, not an enable signal, but an information signal here, okay, instead of an enable, it becomes a demultiplexer. That's it. That's the name for a demultiplexer. So at any given time, your information signal here will be here, will be active here or here or here. Not all of them, but only one of them at any given time, depending on your selecting signal here. That's the idea. So a decoder with enable is in fact a demultiplexer. That's it. So far we have seen what a decoder and a demultiplexer so far. So good. And now let me ask you a question to think about. If you want to design a demultiplexer with enable, what should you do? Just pause the video and try to think about it. Try to draw it with your pen and paper. And that's it. That's the thing about enabling here. So we can implement the combinational logic circuits with decoder and OR gates as well. Okay. Suppose that you can implement that circuitry, or you are forced to implement a given circuitry with decoder only, for example. Let's take a look at this example. What you have here is 4 inputs, and what you have here is 3 outputs here, and you want to implement this circuitry here where you have your 4 inputs and 3 outputs. 1, 2, 3 outputs, okay? So if you want to implement this with a decoder, what you have here will be just having those minterms, or you can also read them from the truth table as well. For example, your P1, okay? You have this 1, 2, 5, 6. You see 1, 2, 5, 6, 8, 11, 12, and 15 connected together here in an OR gate. Those are the cases that giving you P1 as 1. You sum of the minterms here. You make the sum of minterms here. That's the idea. And you do this for P2, and you do the same thing for P4 as well. This is how we do it. This is how you implement it with a decoder. But is this a good idea, or is this the best idea? Now let's take a look at this together. Okay, another one. Like suppose that we're doing this for P1 output, for example. Okay, what you have here will look like this: A7, A6, and A5 and A3, right? Please, you do it on your own as well, and it would be nice practice for you. And this function, namely your P1 function, which was your the A7 or A5 or A3, this odd function, right? So it would look like this when you place them here in their corresponding locations, and the remaining ones will be 0. All right. So if you do a K-map, like a K-map optimization here directly, what will we have here? Let's take a look at this one. These are the best rectangles possible, and let's write them down together like it's a 6, oops, A7 and A5 not, A3 not, okay, plus A7 not, A5 not, A3 plus A7 again A5, A3 plus, so it would be A7 not A5, A3 not. Okay, how beautiful it is. This is this one, this is this one, and this is this one, and this is this one. Okay, that's it. So when you have if you take them in common parentheses, for example, for A7 here, you will have a structure like this or expression like this, A5, A3 plus. If you do this, for example, for A7 not as well, you will have A5 not 3 plus 5 A3 not here. Okay, when you combine them together, okay, you remember them from our previous sessions, right? Well, this is your basic XNOR gate where you have two inputs, and this is your basic XOR gate, right, where you have two inputs. That's it. So as you see in this particular question, the implementation with the complex gates or like the K-map minimization is much more efficient than the implementation with decoders. So your design should take these into consideration as well. Sometimes your decoder implementation can be more convenient. Sometimes your, let's say, straightforward K-map minimization can be much more convenient in this case. Now, what is encoding? Encoding is just the opposite of decoding, where we're trying to convert an n-bit input code to an n-bit output code, where the number of your inputs this time is much higher than the number of your outputs. You're trying to encode that incoming string of information, for example. This is what we call the circuits that do the encoding, and they are called the encoders. Okay, that's the idea. So let's see. Let's try to understand this with an example. Suppose that you're trying to design a decimal to BCD encoder. Okay, it means that, what does it mean? How many inputs you will have here? Like 10. And how many outputs you will have here? 4, for example. Okay, you can implement or depict those input symbols with 4 bits, right? That's it. And your inputs will be 10 bits corresponding from 0 to 9, and your outputs will be 4 bits, namely from A3 to A0, it would be your BCD code. Now, when you try to do this, it would look like this. I mean, your A3, in which situations your A3 will be 1, right? This is what you're thinking about. So let's write them together for all of them. Your A3, okay, let's just write them A3, A2, A1, A0, right? Like you will have here 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? And you will have here 1, 2, 3, 4, 2, 4, 0. 1, 2, 1, 2, 1, 2, 1, 2, 0. Here 1, 0. Oops. 0, 1, 0, 1, 0, 1, 0, 1, 0. Oh, did I do it correctly? Hopefully, I'm not sure. I'm not good. Okay, this one is your 0, 1, 2, 3, 4, 5, 6. Okay, this is 0. I'm sorry. 7, 8, and we missed one of them, which is your 9, right? All right. Now, in what cases your A3 is 0, right? Only this one, like the 8 and the 9, you see? So you write them here. And in what cases, because you OR them together, your A2, okay? In 4, 5, 6, 7, where you see this one, and your A1 will be 4, 2, 3, 6, 7 again, okay, this one, like, and your A0 will be, okay, in odd numbers, okay, the 1, 3, 5, 7, and 9, okay, and then you will have all these together ORed for the BCD outputs. Now you can think that if you combine them, will that result in any cost saving? Of course not, because they're all single lines anyway. You can go ahead and calculate if you want. Maybe you want me to calculate anyway. Okay, let me calculate it for you here. What would be your cost if you do this directly? It would be 2, 4, 5, and your cost will be what? 7, 8, 15. I think it was 15. And if you do this trick here, what was it? Just calling this F1. Okay, and it would be what? 2, 3, 3, and 5. I hope I'm doing it correct. What was the result? 5 and 8, it would be 13, right? But also you need to add this cost as well, which is 2. So it will be 15 again, right? They are the same. So there would not be any cost saving from this, from doing this common factor, like multiple level optimization. There would be no cost saving at all. Okay, now this is the case for only a single one of them is 1 at any given time, okay? Your input digit can be 2 and not the others, okay? Because you cannot input 2 and 3 at the same time into your circuit, right? Here, look at this. Just focus on this. At any given time, your digit can be 9, for example. If it is 9, it means that the other 8 possibilities cannot happen. That's the case with the situation for this type of circuits, where you have only single one of the inputs is 1. Otherwise, you need to implement a priority encoder. Now, it means that more than one of your inputs can be 1, and you need to decide, select between them. It means that some of them should be more important than the other ones, or this is how you make the distinction between them. And when we take a look at a priority encoder example here, exactly this is how it works. A priority encoder with 5 inputs here given here. These are your inputs, and it has 3 outputs, and V is just a check that ensures that at least one of the inputs is selected. This is just a check. So it means that if none of them is 1, your check output or your V output will be 0, and you don't care about the outputs at all in this case. But if any one of them is 1, then your circuit will work and your V will give you 1. That's the idea. And how it works, let's see. If all of these are 0 and this one is 1, this would be your 0, 0, 0 condition. And these one are 0, but this one is 1, you don't care about this D0 anymore, so your output will be 0, 0, 0, 1 case, another one. It means that this D1 is more important than D0. If this is present, this is present, you don't care about D0. if D2 is present, you don't care about anything below it, like D1 and D0. If D3 is present, you don't care about these inputs. And if D4, which is the most important or most significant one here, present, it means that you don't care about the others. You see, this is our design. And how would your implementation look like? It is obvious from this moment that if any one of your inputs is 0, will give you this V signal. It's pretty obvious, right? Your V signal will be D4 or D3 or D2 or D1 or D0. You can write this directly from this truth table, okay, from this table. But I suggest you to make an exercise on simplification with Boolean equations as well. Just try to do this one by one, like trying to just write this like it is either like for all of them you will write this, okay, D4 or D4 not D3, or for this one it is D4 not D3 1, D4 not D3 not D2 plus blah blah. You do this and try to minimize this equation into this one for practice. I suggest you do it. Just pause the video and take your pen and paper and try to reduce this to this one. It's like I think it would be a nice exercise for you as well. Okay, now the thing is, now you can go ahead and have a K-map to reduce them, but if you carefully read from the table here, you can go ahead and do the same for all the outputs as well, all the remaining 3 outputs as well here. Now let's focus on A2, for example, okay? A2 is 1, giving 1 only in one condition, where it is when your D4 is 1. So your A2 is D4, okay? It's pretty obvious, I guess. And what about your A3, for example? I'm sorry, A1, for example, A1. In 2 conditions here, you see, the first one is, let's take a look at this one, D4 not D3 plus, it is D4 not D3 not D2, and that's it. That's what we see here as well. See this one and this one. And what about A0 here? Let's do this together as well. A0, and let me just create some space. And for A0, in this particular conditions, it is giving us 0, so it would be D4 not D3 plus, this one is what? It is D4 not D3 not D1, right? I hope I did this correct. Let's check. See, this one is this one, and of course this one is your okay, since F1 is like multiple level optimization, D2, okay, this was your V. And if you make a, if you have a common factor like this, you can go ahead and go for multiple level optimization as well to reduce your cost as well. But that's the idea with the priority encoders at all. Okay. Okay, now what is selecting? Selecting is like you have multiple inputs and you select one of them and see it at the output. That's it. So it is often used in communication lines and where you want to have the signals multiplexed using the common channel, sharing the common channel. In such type of applications, we frequently see them. They can either be done by 3-state logic gates or transmission gates. So let's take a look at the basic 2x1 line multiplexer. here you have, you see your basic decoder here, and you have a level of enabling circuits and the output here, and now so oops, okay, now it means that at any given time only one of the outputs will be seen, one of the inputs will be seen at the output here, depending on your selection signal given by the decoder circuitry. So if you provide here 0, for example, this one will be selected, this one will be blocked or overridden with 0 value here, and what you see here will be I1, I0, and what you see here will be I0, since it is ORed with 0 here. What you see here will be, and if you give here 1, for example, this one will be blocked and you will see I1 here at the output. That's the idea. And if you want to expand this to 4 to 1 line multiplexer here, again you will have your selecting circuitry as a decoder here, 2x4 decoder here for selection, and your input level should be here, your data level, and this would be your common output here, which would be only one of them will be active at any given time, only one of the inputs. Suppose that, for example, you provide here 1 0 signal, for example, and I think this one, right, based on it's in this value, its index value, it's this 2 should be selected. Let's check it. And at any given time this would be 0, at any given time this would be 1, right, this one. And how about the other one here? You see, this one will be also 1, and this one will be selected, okay, and the other ones will be, okay, not X, of course, they will all be 0 because of the non-selection thing, and this one will be I2 here, and you will see I2 as the output here. This is how basically multiplexers work. That's the idea. And you can also multiplexer you can address or you can send vectors of bits instead of a single bit of information here using this expansion technique. For example, here you see a quad 4x1 line multiplexer here. It means that you have block of 4 words at any given time, and you make the selection so that at any given time only 1 0, for example, 2, only these ones will be selected. For example, if it is, I'm sorry, if it is, for example, 1 0, so this is a 0 1 2 3 information at any given time, for this one will be connected, this one will be selected at all of these levels. That's the idea. Always for example, 1 0 1. So how you connect them? They are always symmetric here, like for let me just try to show you. For this level, y0 level, for example, you will have these here, and for y1 level you will have these, and for y2 level you will have these, and finally for y3 level you will have these. At any given time, this one will be selected, and you will see, for example, if you send here 1 0, for example, you will particularly see the data vector 2 here. That's the idea, rough idea about multiplexer with expansion as well. And you can have other selection implementations where you implement the same structure with 3-state logic gates, and here you don't use AND and OR gates here. As you see, at any given time, for example, 1 0, for example, again, let's do this. This one will be seen at the output. Let's check. So at any given time, if you give here, for example, S1 is 1 here, and it means that this one will be active and this one will be not, right? Because it will be blocked. Okay, and if this one is blocked, let's see that if you have here 0, this one will be active, and if it is 0, this one will be blocked, right? So since this one is blocked, you don't care about what is happening here as well. So as you see, this one is traveling perfectly to your output. Now, what is the cost of this gate? This type of three-state logic multiplexer here, just 14, right? Let's count them. 2, 2, 2, 2, 2, 2. Where you have it's 14, 12, right? And you have 1, 2 here, so it corresponds to gate input cost with nuts 14 here. And what about your other implementation here? Just count the cost here and see which one is more efficient. So it's 2, 2, 2, 2, 2, 2, 2, 2, 2, 4. What you have here, it's 8, 8, 4, 20. And here you have 2 inverters as well. 22 would be your total cost. So it means that this three-state logic implementation has lower gate input cost gate with nuts as well, and it could be more efficient. It depends on your design. No, I think we showed it, and let's go on. So we can do combinational logic implementation with multiplexers as well, and here let's just focus on an example here, which we're trying to convert a gray code to binary code here. Here is your gray code and corresponding binary codes here, and your outputs are in counting order here, and here is your corresponding gray code. So it will just make the transformation here. This is your set of inputs, and this is your set of outputs here. Now it is pretty obvious that your C is seen at the output of X. So it means that your X equals C, but the remaining ones should be done carefully. As a first step, we should order the inputs first. Okay, let's order it in input order. So it would look like this. Okay, we just make the ordering here, and these are the corresponding binary outputs, of course. And now we will use again X equals C, but for Y, we will send the select signal from ABC, and these will be the corresponding inputs that only one of the outputs will be seen at the output depending on them. You see, you put that line here for Y here, exactly this one. See, this one, this Y column will be here, placed here, and your selection signals will be sent from here, and at any given time your output will be this one. And again, your selections will be coming from here in this 8x1 multiplexer. And what should be your data inputs here this time? These ones, right? For Z corresponding, and at any given time, based on your selection, only one of them will be available at the particular output here. Now this pretty looks like fixed inputs is identical to a read-only memory with 3-bit addressing, where you do this addressing with 2-bit data here. Okay, these are your data, 2-bit. Okay, at any given time, these 2 bits are addressed for the output. You see, so this is your 2-bit data here, 2-bit data here, and it looks like a read-only memory approach to this design. Now there is also another approach which could help you to cut down the cost, where you do some trick to get this cost. Okay, again, this one is pretty obvious. Like if you first order them again in gray to binary order here, like this should be in this order. So here, when we first order them, this one, okay, you see that this one is in order now, and these are the corresponding binary values here. Look at this, how beautiful it is. Now again, your x equals c from these columns. All right, no problem. Let me just change the color here to red now. Okay, now look, at any given time I limit this selection with those blocks. It's lovely. Okay, and what you see here is dependent on x. What is this? It is c. And for any given time, what is your output? Again, so for it's 0, 0, it is c. For see, like let me just try to do this. Oops. Step by step. So this one is, as you see, it is c. And for 0, 0 again, what is this? The output will be again, this one again is c. So that's it for 0, 1. So this should be, look how it is inverted. Okay, it is c naught, see? So here you have this as c naught, and this one is again c naught. And for this one, if 1, 0 is selected, so it would be again c, same, and this would be c naught, and this one again c naught. If finally, if it is 1, 1 is selected, and this one would be c as well. So in the end, you have this set of inputs here. Now you can implement this with 4 by 1 multiplexers, right? Where you have 2 inputs here, A, B, and your 4 inputs will be corresponding for Y should be this column, and this column for the Z outputs. And let's see, you have this provided for Y here, and these are your selection inputs, and you have this for Z as inputs, and these are your selection inputs again. So you see that the cost of the circuit is almost cut down to half here, and this is a much more convenient and efficient implementation of this circuitry. But this structure is no more read-only memory like. It's something unique to this type of implementation anyway. Okay, so far what we have seen, let's just is that shortly. Like what we did today is in this session is we talked about the decoders. Like the decoders are where you have like you select only one of the outputs, okay, like the 3 by 8 decoder or something like this. Select and only one output. Okay, this is how we can summarize this. Encoding is like encoders. We represent information with less bits, information with less number of bits. This is what we call encoders. Like because we're encoding them, the moment of encoding. And multiplexers is what we just discussed a few moments ago. Only one input is shown at the output. Only one of the inputs is shown at the output. Like you can have, for example, 8 by 1 multiplexer, for example, MUX. We call them MUX. And these ones are called decoders, multiplexers. And what is the multiplexer? The multiplexer, we just seen this as a decoder with enabled, right? And it does, what it does is, like, in fact, only one input is shown at the single output, I mean, you have only one input here, single one, but it can either come off from here or here or here or here. That's it. That's the idea. So we can say that the single input can be read at only one output here in the demultiplexer. So you can have, for example, 1 by 4 demultiplexer, for example, and this is how you you have the abbreviation here like DMUX. Okay, and okay, this is what we discussed so in this lecture, and thank you for listening.